Good afternoon and welcome back to the Calculus Reading Group. Today we have a speaker who may be familiar to some of our audience, Ryan Turner. Ryan did his graduate studies at Cambridge University under the supervision of Zobin Garamani, where he studied Gaussian processes and change point detection. As some of you may know, after completing his PhD and prior to joining the industry, Ryan spent a year on the IDT team here at Mila, where he worked on tools and benchmarks for machine learning. Today, I am pleased to welcome him back to Mila to discuss his recent work on second-order gradient methods, a topic of particular interest to our reading group. Despite leaving us for greener pastures, Ryan continues to actively publish on probabilistic modeling and participate in the machine learning community. In addition to his recent work at Twitter, he has co-organized a number of workshops, most recently the Black Box Optimization Challenge. And Ryan also lends his talents to improve the usability and explainability of machine learning tools, from hypothesis testing to model explanation. Outside of his research activities, Ryan is an avid outdoorsman and mountaineer who has climbed some of the highest peaks in most, if not all, of the national parks in the continental US and Canada. Please welcome Ryan Turner.
Thanks for that. Thanks for that good introduction. That's a lot more details than I thought you'd get to. It's like, oh man, it's pretty good. All right. But yeah, thanks for all that. Yeah, so I guess it's just a small group today, so don't feel shy to ask any questions if there are. So probably, it's not like you gotta be worried about time or anything like that. It's also I think the material I'm going to go over is a lot more, maybe it might be more simple and not as much theoretical complexity as some of the other things I saw in the when I was looking through the rota of different things being presented in this reading group. That some of them were maybe had some more subtleties to it. So this should be easier to get through. So it's not to be too worried about getting through the material. So this is something that we've just going to be talking about, a tool called Dict-minimize, which is a tool we open sourced at Twitter. I developed at Twitter last year. I was working on it for a little while on the side, little by little. And then towards the end of the year, we open sourced it and we just published a blog on it. So I'll present it here with the little Twitter logo, Twitter Cortex logo. So we'll get to it here. So it's about second order optimization methods. And this is like some of the background. So yeah, I've been in machine learning a while, doing machine learning a while. So I sometimes reflect back to the old days and just sort of rewind the clock here a bit. So if we think back to over like 10 years ago, before everything was in the current paradigm of deep learning and SGD and all this kind of stuff, methods like LBFGS and conjugate gradient were sort of the go-to method in the in the old days, before deep learning. And even if you were training a neural net, that was probably what you were using. And if you think back to say like pre-2010 or so, not only was it not like everything was deep learning, but also a lot of stuff was like in MATLAB before, and that before Python started making the kind of everything went to Python and took over about 10 years ago. And in that older time, there was this thing called minimize.m, which is what my advisor wrote when he was in Jeff Hinton's lab, maybe like 20 years ago or so. He wrote this thing called minimize.m, which was a MATLAB routine to do optimization using conjugate gradient. And there was a time there, like for 10 years or so, that was like the default. Everybody used that when they're optimizing anything. And that's like what everybody did in machine learning, was to use, okay, we're going to do conjugate gradient using minimize.m. It was a slight variation on conjugate gradients, but it was sort of sort of what it was, right? A couple other bells and whistles thrown on, and that's what people did. Maybe up until 10 years ago, that was sort of the default approach people took. And then, you know, everything changed. Two things changed, as I was saying. Everything switched. Python became the dominant language in machine learning, and it still is today. And then, of course, you know, with deep learning, everything started changing to going to that sort of deep learning type of framework. And so there was an interesting thing happened with deep learning. So you know, earlier in the old days in neural nets, they would often train them without SGD. They would get the exact gradients on them because they were training on much smaller data sets. So if you go back like, you know, 20 years ago or something, that's what people were doing. But of course, what happened was that as the data sets got bigger, and then which deep learning was excelled on, you couldn't compute these exact gradients anymore because it was just every time you took a gradient step, you're summing over such a massive amount of data. It just became like this compute bottleneck. So people started randomly subsampling the data and getting stochastic gradients that were like unbiased estimates of the exact gradients, and then just optimizing using these noisy stochastic gradients. And I think with sort of the miracle of deep learning, I'd say, is that it turned out that for a lot of these deep learning problems that people were doing, these noisy gradients actually worked better than the exact ones. So they were both, it was like a win-win. They're actually cheaper. They were cheaper to compute. In fact, they were like the only option to compute, but they actually worked better for a few different reasons that I think is probably still not, there's probably not universal acceptance on exactly why they work better, at least as far as I know. But I mean, there's different theories people talk about things about loss landscapes with saddle points and the noisy gradients that escape saddle points. There's also a lot of talk about implicit regularization because they are actually not very good optimizers, things like SGD, and that, but maybe that instead of being a bug when you're training neural nets, that actually is a feature instead of a bug, because that sort of regularizes your thing. So there's a few different explanations. There's probably several others that I'm not even mentioning right now that I forget off the top of my head, but there's all sorts of reasons why they say, you know, SGD actually works better for this deep learning. And that's all, you know, a lot of the things that are sort of the miracle of deep learning and like why things like really took off and started working really well and sort of deep learning took over the last 10 years. All boils down to this, I'd say. Well, I mean, you know, GPUs and all that kind of stuff too, but you know, can't boil it down to these 2 bullet points, but you know, you get the idea, right? But I think one of the things I want to talk about in this talk, though, is that, you know, optimization is a much broader field than just training the weights of a neural network. Right? It's been around a lot longer, and it is much broader, used by a lot more people on a lot of different types of problems. And a lot of times with people who make like these autodiff frameworks, like people working on TensorFlow and PyTorch and so on, they probably also forget that too, right? They forget that there's also other use cases besides just training the weights of a neural net, right? Because it's very easy to become hyper focused on that because this is sort of like such a big use case these days, right? Especially if you're implementing something in Python, because that's where one of the big users of Python is deep learning, right? And as I was saying before, one of the things with SGD is that SGD is actually, in some ways, can sometimes be a bad optimizer. But that feature, I mean, that bug has to be a feature for in learning problems. But you know, if that's in some cases that's not a feature, it's actually a bug. And when you have exact gradients available, a lot of these traditional optimizers can work better without hyperparameter tuning and other tricks like gradient clipping, gradient norm. There's probably like 20 different tricks people do a lot of times. And also, even if you're not doing any gradient tricks, a lot of times there's still hyperparameter tuning with like learning rate and all this kind of stuff. And usually with these newer methods like SGD, you have to tune these hyperparameters to make them work. They don't work very well. Default, there's not like universal hyperparameters that work pretty well. Whereas a lot of times these traditional optimizers, they have hyperparameters. There's always hyperparameters, but usually just the out of the box ones work pretty well. And I know here's an image that was from back in NeurIPS 2017. This Rahimi and Rec, I think it was like a keynote or some sort of talk, some sort of invited talk they had. It was kind of it was a controversial talk for other reasons, I think. But one of the interesting slides that stuck out to me was they had this one problem, which is maybe a bit of a contrived problem and maybe not that interesting, but it's an interesting example, I think, still, showing about how like some, these simple gradient descent methods don't work very well, but they were able to apply a more traditional optimizer and it worked really well to optimize a particular problem, whereas like SGD just kind of gets stuck, or Atom too, all that stuff, right? And finally, one other point is also handling constraints as well. A lot of these methods have been developed to handle sort of constraints and bounds and stuff like that pretty well, the traditional methods. So examples of when you might want to do some more traditional optimization instead of like a SGD, include sort of like a calibration layers, at least in deep learning, because a lot of times the calibration layer, you have maybe a simpler model with a smaller data set. A lot of times if you have like a held out data set to calibrate the probabilities from the output of a neural network, it might be it's typically a much smaller. You might have like a couple thousand points or something. And therefore you don't actually need to, do the stochastic gradient stuff. You can do exact gradients. I'll show an example of Deep Dream and adversarial examples, because there you don't need the whole training set to compute the gradient. You're taking the weights of the network are fixed and you're optimizing the input. So you have some examples of that here as well. And then of course there's sort of the general world of like just optimizing some sort of action. Like at University of Montreal, I know before they were famous for deep learning, they're also famous for OR, or operations research. And of course, there's a lot of optimization problems that don't fit in the usual paradigm of, optimizing the weights of a neural network, right? So like, if you have some model the different risks of different assets, maybe you're trying to like you might be doing like a portfolio optimization. It's just like one random example out of like thousands I could pick of a general sort of optimization problem that's different than training the weights of a neural net, right? So in all those examples, those could all come in like this motivation. So basically use some cool objective function. Hopefully it's a cool objective function. But so it's unlike when you're training the weights of a neural net, it's a function of the entire training set, which might be giant. But let's suppose we're optimizing a function that's not a function of the entire training set, which such as all four of these here are just for random examples of cases where you don't have to consider an entire giant training set to compute your objective function. Maybe it's a very complex system. Of course, nowadays that's not an issue at all. You have all the good autodiff tools, so even if it's a very complex and crazy objective function, that's not a problem. Such as in an adversarial example, for instance, where you're optimizing, you're backpropping through a network. It's kind of a complicated function, but it doesn't matter. Sometimes a problem might have weird conditioning, like condition numbers and all that kind of stuff. Maybe you don't even know if it's weird or not. And a lot of times that might throw off first order optimizers, but and you may not even know if you're in that situation. But that's not an issue, because we can just use better second order optimizers, and we can it's not an issue because we can get the exact gradients. So the big issue with second order optimizers in general, or these traditional optimizers, is they don't play well with noise in the gradients, right? But if we're in a situation where we can get the exact gradient, we can use these traditional optimization techniques. And that's what we have here. But we have two options. There's two different worlds basically prior to Dict-minimize, right? I call it the old world and the new world, right? So in the new world, such as like in TensorFlow or PyTorch, they include different optimizers. There's certain recipe optimization loops that you can run in PyTorch or TensorFlow with like SGD or Atom is usually the two defaults, and there's a few other ones in there too, but they're usually all variations on the simple gradient descent, first order gradient descent. Typically, you have to do a lot of tuning on the hyperparameters and often some tricks, like I was talking about before, with like gradient clipping and all this kind of stuff. Often, on many problems, you have to apply a lot of these various tricks to get the optimizer to work well, and you don't really know a priori which tricks you should use and which tricks you shouldn't use. And sometimes it requires a bit of experimentation. You got to kind of play with it, try it a few different ways. And eventually if you try it a few different ways, it might work well. But there's a lot of things to play with to get it to work basically on many problems, right? But then there's also the old world of SciPy optimizers. So has many different optimization algorithms. They're a lot more principled, like theoretical guarantees and all this kind of stuff. Really good support for constraints and bounds, even very complex constraints, saying like some it has to be, you have some feasible set of the inputs. But the downside of the SciPy optimizers, it only optimizes vectors. It has much simpler problems in mind where you have to have a vector. It's not like these new optimizers, which can handle simultaneously optimize several different parameters, which could be arbitrarily shaped tensors, which is really what we want. SciPy is just old school, maybe closer to the math of optimization, where they always assume you have a vector. So basically, it only optimizes vectors. So that's kind of a hassle. And it also doesn't really interface very nicely with like TensorFlow and PyTorch because it predates all those tools. In fact, a lot of SciPy is like wrappers on Fortran routines and stuff like that from the old days. So it assumes you were writing the gradients manually, doesn't play in it, you can't just pass it TensorFlow stuff, objects, it just doesn't work. So it's kind of a hassle. So that's the trade-off. You kind of got to, when you have a particular problem, you got to decide which world you're in, right? So of course, if you're training a deep network, I think without hesitation, I'm in the new world, right? No issue, right? It's without hesitation. It's like, yeah, I'm in the new world, right? On the flip side, say the portfolio optimization, which is maybe you have some variation on like a quadratic program or something like this. And maybe you could easily write the gradients manually for that. Maybe it's kind of weird condition. In that case, you could say without hesitation, I'll try the old world, right? Like SciPy optimize, right? Like these sort of operations research type problems. It's like, okay, I'm in the old world instead of, SciPy. I mean, instead of like, okay, we're training a deep net. Okay, that's new world, right? But I think a lot of times you'd really like to have the best of both worlds. And that's what Dict-minimize gets you, right? Instead of having to pick between the new world and the old world, I want the best of both, right? That's what I want. So like if you're in Python, which, if you're a machine learning researcher, that's basically for certain. Then SciPy is the sort of go-to if you want to do something beyond just the simple sort of gradient descent. So there's this SciPy.optimize.minimize function, which does optimization in Python in a SciPy import. It's pretty well. It's pretty tried and true. Some of these things are wrappers on like old Fortran routines. They've been around for decades, and like they sort of have like hyperparameters built in there somehow still, but they've been like tweaked over the decades because like, there's a lot of experience like built into it, right? So like they do work pretty well out of the box, with exact gradients, because they weren't designed for noisy gradients. This is the trade-off, right? If you got exact gradients, they work really well out of the box, usually. So they usually assume the form you have f of x. This is the function you're optimizing, but x is very constrained. It has to be a numpy NB array of shape n by 1. It's super picky about that. That's the only thing you can do. A lot of times, some of these optimizers will even crash if you pass it a float 32. It has to be a float 64. Like, it's that picky, right? So you have a very limited interface, but if you can get it within that interface, it works well. What we want is the interface that TensorFlow and PyTorch give us, the way that we work now, where a lot of times, say, like in PyTorch, you have like usually a parameters dictionary, right? When you have like a PyTorch object, which tells you all the different, so you have like a different names of parameters. So like this might be weights 1, weights 2, and you can have arbitrarily shaped tensors. They don't have to be vectors. They can be of any shape. You know, it can be a 1 or 2 dimensional, or it could be a 3-dimensional tensor, whatever, right? Yeah, and that's what you want. That gives you the flexibility you want as a researcher, right? To be able to optimize objects like this, right? You don't want it to have to be forced to be like this. So in SciPy, you gotta go through this repetitive hassle every time. You gotta pack it into a vector, unpack it. You gotta convert to NumPy, because you're in TensorFlow, you get the gradients as like this TensorFlow thing, and you got your in PyTorch thing, you know, and you gotta like do a detach and all this kind of stuff. You gotta always like pass it back and forth, and it became this like repetitive hassle. So basically, Dict-minimize takes care of all that crap for you. Makes it easy. Yep.
Just a quick question here. In the beginning, you mentioned that one problem is stochasticity, and I was wondering if you could give some intuition for why that breaks these old world optimizers.
Yeah, that's a good question, and I think it's a very complicated question. Some of these optimizers might work okay with a little bit of noise. The folklore used to be like you couldn't have any sort of approximations when you were computing your gradients, because like any error at all, like even some like 10 to the minus 6, like tiny little bit of error from some sort of approximation, your gradients would just totally destroy the whole thing. That was sort of the old thinking back then. But they might not be that sensitive, but it makes sense though, because a lot of times gradient descent, it just takes one step, a step and a step and a step by every gradient you get. These other tools do a lot of other stuff. Like they'll do steps like that. Then they'll also do these things like line searches, where they'll like go out in a certain direction and like search along that line. And they have like certain like stopping criterion based on all the sorts of theory and optimization about like if the gradient gets too big in this way, like I can do a line search out here, and then I know I can stop when I get to this point and then start doing gradient descent again. And like all that stuff has a lot of like, you know, decades of theory like motivating how it's done. And I think a lot of the problem with that is all that theory for some of these methods was designed from the point of view that you can get the exact gradient. Potentially you could soup these methods up to somehow accommodate stochastic gradients. Although who knows? I mean, I don't know. I mean, maybe if you have really noisy gradients, maybe there's not much benefit to be had. Maybe you should just be doing SGD or Atom, right? Maybe. It's an open question.
Yeah. I mean, it sounds like there's different kinds of stochasticity that you'd like to manage. Maybe the intrinsic stochasticity of computing gradients on a computation graph, and then there's the stochasticity that emerges from kind of sampling or subsampling from this data set. So.
Yeah. Yeah, both of those, the data subsampling, I mean, that's the traditional source, but yeah, you could also have like, I guess like in VAEs, for instance, if you train a VAE, usually you approximate an expectation, which is the random sample. And that's a source of stochasticity that's not from data subsampling. But, you know, yeah, I don't know if these methods would work well with that either. I think I would guess that both sources kind of mess up these methods, would be my guess. But I don't know. I mean, I think they might be more robust to the noise than the folklore suggests. Like, that was always the line. It's like you need really exact gradients if you want to do this. But it might be you might still get a little bit of traction, even with something with a little bit of noise in there like that. So it'd be interesting to do it'd be interesting to see some experimentation on that to sort of really see what the breaking point is. Like how much noise can you put into like LBFGS before it just breaks and you should just be doing SGD instead, which is, I think, most deep learning training is probably beyond the breaking point, and that's why people don't use LBFGS for training, big deep networks. But it'd be interesting to understand better where the breaking point is. At least I don't understand where it is. I just understand the dichotomy of exact gradient, stochastic gradient. That's my understanding of it. But anyway, so we got the Dict-minimize tool, which tries to give us the best of both worlds. And it gives you interfaces to basically all the different tools that people use, at least open source tools. So you have the TensorFlow, PyTorch, JAX, and NumPy, which with NumPy, you don't need to do any conversion between NumPy and NumPy like you do with the other frameworks, but you still want to be able to optimize a dictionary of parameters rather than a single vector. So that's why you still need a NumPy API. I don't have a Theano API. I don't know if at Mila people still use Theano. I know when I was at Mila, things were kind of in flux. I know some people are still using Theano, and some people had gone to PyTorch, some had gone to TensorFlow.
Interestingly, yeah, there's been a reemergence of interest in symbolic gradient computation, but I'd say that's not directly here at Mila, but from Python scientific meeting.
Yeah, I remember when I was at Mila, things were in flux. So anybody who'd done an internship at Google was using TensorFlow, and the other people were still using Theano. I think that's sort of the state of affairs back then, a few years ago, a few years back. But anyway, if you can get exact gradients, then you can try it out. Try out Dict-minimize. There's usually no hyperparameter tuning required. There are hyperparameters to tune, but people usually don't tune them. They usually just works anyway, and no tricks to manipulate the gradients. And I think just the final point that I've been noticing is that a lot of times when I've tried to apply this internally, everyone's just been so conditioned to use SGD by default, just because that's what people are so used to now, and it's just people are use it for every single problem. But there are alternatives that are applicable in certain situations, and I just always remind people to try out the alternatives when they're there. So basically, the other thing I wanted when I did Dict-minimize was to make a very simple API. So with SciPy, you can do SciPy.import, SciPy to optimize import and minimize. And I just changed it to, depending what framework you're in, you just go to either Torch, TensorFlow, JAX, NumPy, and just import that corresponding API to get the alternate minimize function. And it mirrors, not identically mirrors, but it's very similar to the original SciPy minimize API. It's not identical because part of the point is that we can optimize dictionaries of parameters. So we don't want it to be identical, but it sort of otherwise mirrors the original API of the SciPy one. But so it's very similar, but not identical. So now we have some examples of all four frameworks, the Rosenbrock, or variations on the Rosenbrock function, which is sort of, people are probably familiar with, but it's sort of like the MNIST of optimization, where it's a simple problem by today's standards, but is also just a very common example just to use as a demonstration purposes, even though, you know, it's a simple example. And then we'll get to a more complicated example next. So yeah, so I mean, first, I guess what people are probably most interested in PyTorch. So I'll just, can you see the notebook here? Is it good?
Yeah.
Yeah, okay. Yeah, so basically, yeah, so instead of SciPy minimize, you just go torch, Dict-minimize.torch API, import minimize, and that's all that's the main change you have to make compared to using SciPy. We're gonna try different optimizers. Here I have, I've coded up a variation on the Rosenbrock in Torch. Somewhat arbitrarily broken it into 2 different parameters just to demo the capability to optimize 2 parameters simultaneously rather than just one variable for demonstration purposes. Also a shift parameter just for demonstration purposes to show that we can how to pass in extra arguments just for demonstration purposes. And yeah, so this is like you get some random initial parameters, and then you just call minimize the same way you call SciPy's, which is you just pass in the objective function, so it's the objective and the gradients. The initial parameters, if you have extra arguments, you can pass them in like this. Tell it which method, so it's just one of these methods. So these are the traditional optimizers, conjugate gradients and BFGS, some quadratic programming stuff, SLSQP, whatever that stands for. SciPy also supports this callback thing, which is optional. I use it here just to log the history of progress. That's optional. And then I show the performance of the different built-in optimizers. It's not meant to be a rigorous benchmark because I don't like average over different starting points and stuff like that, but it's just a demonstration of what you can do. Again, basically, I have another notebook here for using the TensorFlow API, same story, just import Dict-minimize.tensorflow, import minimize. The rest of the code basically looks the same, except the objective function here, now I've implemented it in TensorFlow instead of implementing it in PyTorch. Same story, random initial parameters, call the minimize function. Basically for TensorFlow and PyTorch, this line of code where you call the optimizer, it's identical. This is basically an identical line of code, regardless whether you're using TensorFlow or PyTorch, because I've implemented the same API in multiple frameworks here. So you just change this, just change the import. Otherwise, this is identical. Just ran it again in a different, just the other implementation. Same story. You got like JAX. A lot of researchers like JAX. I like JAX. I got a JAX API here. So from Dict-minimize.jax API, you can import minimize. Implemented it again. I do like to point out in this comment here that JAX makes the getting the version of the objective function with the gradient simpler than any of the other ones. You just call value and grad. I do like to highlight that because I do like JAX. And then, of course, it does have this random number weirdness, which bugs some people. It doesn't bug me, but some people do get bothered by it. Yep, same thing in JAX. You just call the, again, same exact line of code, whether it's, you had PyTorch, TensorFlow, JAX, call and minimize exactly the same, just change the import statement. This was a slightly different objective function, so the curves don't look the same. So this one's actually a little bit more interesting because I think it's a bit harder. This objective function is a bit harder. I think it was a higher dimensional case here. I think this is 8 dimensions instead of 4. So here you can see a bit more of them where some of the optimizers kind of struggle, like they kind of get stuck. And you can see that BFGS works pretty well. Conjugate gradient works pretty well. It's not converging as quickly as LBFGS. And this is an interesting curve to compare the performance. Finally, same thing in NumPy. import minimize from the NumPy API. Slightly different objective function again. See, BFGS works pretty well. Conjugate gradient gets stuck on this other one. And same line of code. So that's all there is to it in the examples. Works pretty well, pretty simple. Should be simple. I hope it's simple. If you're familiar with the SciPy interface, it's easy. Right? You just have a function that returns the value of the objective function and the gradient. You pass that in here. Pass your initial any initial parameters. This is your initialization. You pass any extra arguments. So these are extra arguments to the optimizers that are constants, not that you're optimizing. These are just constants. Pass them in here. Here you select your method. So usually it'd be one of these, but there's more options too. And then the callback. Usually you don't use one, but that was just for logging purposes. And then you get this. Then you get when you can try out all the different optimizers. So yeah, that's the story there. And then that's all I'm going to show for the basic usage. Is there any questions on that there? Is it good?
I don't know if the audience has any comments or questions, but I know I have a few.
Oh, okay, you got a few questions. Okay.
So I don't know if you could comment on how difficult it was to implement these different optimizers in these different frameworks, and what are the advantages of in terms of computation?
Yeah. Okay, that's a good question. So I did not attempt to re-implement these optimizers because they have been so honed over the decades. So basically, I have a wrapper that converts the data to NumPy, packs it into a vector, runs the SciPy optimizer, and then converts it back. So it's basically a wrapper. I didn't attempt to re-implement it because I think, like, for instance, with PyTorch, they did attempt to re-implement some, like, the SciPy one directly in PyTorch natively. I think it has a reputation that doesn't work very well. So I just tried to avoid that. I just wanted to use the original.
Okay, I see. So you're using the existing implementation.
Yes. So yeah, it's exactly the same, because all these optimizers would be quite difficult to. I mean, maybe if I just picked one of them, I could re-implement it in all the frameworks. But then you have like a combinatorial problem, right? You have like all the different optimizers times all the different frameworks. It just got to be too much, right?
Yeah, because I know there's some maybe numerical issues when you mix NumPy and some of these frameworks. But it sounds like this, well, I mean, at least you can compare their efficiency, say in JAX or in,
yeah, there might be some numerics. I don't know if there's any sort of ways to avoid those pitfalls. I know, again, as I was pointing out, like some of these optimizers expect float 64. So I did have to do like a conversion to float 64. Like a lot of times what comes out of TensorFlow by default is float 32. So then you have to like do a conversion to float 64 and convert it back. So hopefully there's not any issues with that, but that's an issue. Again, if you're doing stuff on GPU, that can be a bit of a hassle, because that does mean it has to go to CPU. But the final result, hopefully the final result is not too ginormous that introduces much overhead. Because, even if all the intermediate computation is on GPU, if it's just the final computation of the derivative that needs to be put back to CPU, hopefully, unless that's some really enormous dimensional thing, that shouldn't be very much overhead. In my examples, they were just CPU examples, but you could use it on GPU as well. So yeah, that's the example there.
Okay, and then I don't know if you probably have some more to discuss here, but if there's questions.
Yeah, I have. I want to talk about Deep Dream as well, which is our final. This is the final example I'll show about using Dict-minimize. But that is. But yeah, if in case there's any other question, then I can go over that on the stuff with the other problems, the simpler ones I already showed. Did you have another question? Or should I just go to the Deep Dream?
I don't see any in the chat, so maybe.
Okay. Let's see. Okay, so going to Deep Dream here. Deep Dream, that was another example I said we could use this tool. So basically we optimize the response of a certain neuron, of a single neuron in an inception v3 network with respect to the input image. That is the concept behind Deep Dream, if people are familiar with Deep Dream. And you sort of visualize what a particular neuron is sort of responding to. And that's sort of the idea. Now, although inception and these big other, deep networks for images were trained on gargantuan data sets, the issue with these here is that we're treating the weights as fixed, right? Just like in adversarial examples, you treat the weights of the network as fixed and you optimize the input, not the weights of the network. Therefore, because the weights are fixed, there's no big data set to deal with when computing the gradients, and therefore we can get exact gradients. You don't have to get like you don't have to do any data subsampling and get a stochastic gradient, right? So you can get the exact gradient with here. Here in this example, we're optimizing some mid layers in Inception v3. This is taken directly out of a TensorFlow demo, which is popular, and which is from the inventors of the Deep Dream stuff. Some of the middle layers of the network tend to respond to textures. I guess as you get deeper, they respond to higher level concepts. So we're kind of going to do an optimization of an image to texturize it in effect with Deep Dream. Another advantage, some of the advantages of using Dict-minimize for this over using just simple gradient descent like they do in the TensorFlow demo is that there's also built-in support for bounds and constraints. So basically every pixel has to be between 0 and 1, as in it has to be between white and black. And with using their method, they always had to do all sorts of clipping to move it back into the feasible set, whereas bounds can be supported explicitly in a principled way when you use the traditional optimizers. Also, there's no gradient clipping tricks as well. Like to get their example to work, I think they used both gradient norms, so they had to renormalize the gradient, and then also I think they applied a little bit of clipping to the gradient also. It's, it works, but like a priori, like, you might have to play around with it a few iterations to know that that's what you have to do. It requires these kind of tricks. You might have to iterate a few times to get it to work. Whereas the LBFGS version, you just throw in the actual real gradient. You don't manipulate it. You just throw the real thing in, and you don't manipulate it with the hyperparameters. You just throw it in and use the defaults, and it works. So it's sort of like a just works kind of thing. That's the primary motivator for this package. It's a just works thing. You don't want to play with it. Like you're always like trying to play with okay, tweak this, tweak that thing. And I don't want to tweak anymore. I just want it to work. That's what this package is for. So here we texturize a Labrador retriever. We initialize it with the real image of a lab. That's a real Labrador retriever, and we texturize the image to maximally the output of a particular neuron in Inception v3 in like layer 3 or something, I think it was. And it looks like that neuron responds to sort of these crocodile type textures here. And this is what happens. It sort of gets these weird, or maybe these sort of crocodile textures, these sort of bacon strips kind of in the fur. You kind of see here. So here's the blog post. We made a video comparing LBFGS on the right and SGD on the left per function evaluation. And you can see that on the right, LBFGS is the effect kicks in much faster per function from a per function evaluation point of view. It kicks in faster. And that's also, we can quantify that by looking at the objective function we're optimizing to see that this is the objective function. We're trying to optimize the deep dream, which is the activation of a particular neuron in the network. And you see that that's interestingly, LBFGS is actually slower at first, a little bit slower. I'm not sure why, but as it sort of builds up that second order information, it gets faster in the end. And this is quantitatively, and this just shows visually the same thing you see in the video, which is it texturizes it in less function evaluations of the inception network. And that's basically it. I'm going to wrap up here with just a pip install Dict-minimize recommendation. Here's how you use it. There's the GitHub page over here. So here's the GitHub page with all the examples included, instructions, read the docs, documentation. If you want, this is also if you have any, you want to know how to use it. We got the documentation, SciPy, and then of course also we have a blog that we just published last week, which basically goes over the same material I just went over in this presentation. You can read about it all here in the blog post. So that's that's basically it. That's it there. And then wait, so present. Okay, so I need to get the yeah, there you go. You have the right background. But yeah, that's all. So
yeah, thanks. Let's give a round of applause to Ryan for giving this great presentation about Dict-minimize. You can unmute yourself.
Yeah, we haven't quite figured out the whole applause thing in the Zoom world yet, but we have to. Everyone has to. Yeah, it's like you kind of like, oh wait, should we mute? I'm mute. Oh, I'm too slow. Too slow. I missed it. That's what happens to me. I'm like, oh, I missed it. I was away from my computer. But anyway, yeah. So that's the story there.
So I don't know. You're at 50 minutes now. If you have like a couple minutes for questions.
Yeah, I think I might have to stop around 1 West Coast time or 4 on the East Coast. But yeah, I got a few moments here. If anyone has any questions, or I don't know if they want their 10 minutes back, but.
Well, one of the things that I was curious about, and I know that you have a background in probabilistic modeling. One thing they're concerned about is the manifold, whether it's centered or not. The distribution that they're studying might be non-centered or centered. In one of the presentations we looked at, reparameterization, and this came up. Well, do you want to reparameterize the natural distribution into something that's more easy to optimize, or to add some more flexibility to your optimizer? I was wondering if you see a way to do the former in a framework like this, where you have something like a library that you can give to users to automatically.
Well, you mean like things like standardizing the data and stuff like that, which usually helps a lot in like deep learning, right? And Yeah, I think this is going to be a lot less sensitive to whether or not you standardize the data or things like that than say like a simple kind of gradient descent, which could be like super sensitive to it. That said, I think it probably still it works better. Just like if nothing else due to like numerics. I don't think it has a complete invariance to rescaling with most of these second order optimizers. I think they attempt to have a sort of invariance, but I don't think they do exactly. So things like the sort of Newton type methods, which is where you invert the Hessian. If you do like a exact Newton's method, then that provides a lot of invariances, right? Like you have invariances to rescaling or rotations. You can even have an arbitrary rotation of your parameter space, and you'll still get the exact same answer in the end, and it will work just as well if you were to use like a full Newton method. But that's even within Dict-minimize, people typically would not be using a full Newton method because then you have to compute the exact Hessian and invert the exact Hessian, which is just like such a huge compute thing that they use things like basically LBFGS and conjugate gradient. What they do is that they only use the first derivative. They don't use the Hessian, but they kind of attempt to approximate. They sort of attempt to approximate the Newton method. Is sort of the way they're inspired as. Like they're kind of build up an approximate Hessian as they move along by getting several first order derivatives. So that's sort of the inspiration behind them. Like a lot of these methods treat a full Newton where you invert the Hessian as like the gold standard that they all try to approximate. Anyway, I don't know if that's kind of a rambling answer there, but
to take up too much time from the other questions.
Yeah.
Yeah, I have a question.
Yeah.
So thanks for your great talk and nice library. And actually, I really understand the problem you face first when trying to. So I think the main issue is that when we write mathematics, we work with parameter vectors, say. But
Yeah.
these vectors are not actually vectors. These are sets of weight matrices and bias vectors, and yeah. So it's kind of very easy to write, I don't know, parameter update. So you just write some parameter minus learning rate times some other parameter, or something that looks like a parameter, which is the gradients of the loss with respect to parameters. So basically what you do in your implementation is to go back and forth, if I understand correctly, between this set of tensors, say PyTorch tensors, for instance, and one flattened NumPy vector.
Yeah,
and
that's what happens. There's a pack and an on-pack operation. You have to pack everything into a vector and then you got to unpack it back to the original. So there's a little bit of bookkeeping involved, but
yeah, and I've had similar issues with this kind of thing. So I was wondering, apart from this adaptation, say, of the SciPy minimize library, do you have any other applications of this kind of your libraries to other libraries, say, or to other? I don't know.
Yeah, that's a good question. I did implement things in a way that attempt to be a bit general. So there's like the front end and back end. Hopefully you can have like any combination, right? Because the front end is either PyTorch, TensorFlow, JAX interface, and the back end being, right now, the only option is SciPy. But in principle, we could allow any combination. I don't know if I haven't found of any other packages, at least in Python, that are worth interfacing to that I know of. But there might be. There might be some other ones. But in general, I haven't really seen the need to interface to anything else. I mean, other than what's already built into TensorFlow and like PyTorch, right? But then in which case you don't need Dict-minimize, right? Because you can just use it directly. So it would be something like a legacy backend, which was, something like SciPy, which is all like, NumPy code that you need to implement, you need to interface to. And I don't really know of any. Well, I mean, I'm sure there's some libraries out there. I just haven't had the need for it, basically. But I mean, if you have, if anyone has any suggestions, like they want to be able to interface to something else, or they want something else on the back end of a different optimizer or a different framework on the front end, like say somebody wants Diano. I haven't had anybody request Diano, but like say somebody did. They could always put a GitHub issue and pull request. I don't think many people use Diano anymore, so I don't think people are going to request it. But yeah, something like that, right? You know what I mean? So if you can, if anyone wants wants anything like that, I'd be interested to see it on the GitHub issues page and say, or make a request for, I want to interface to this or that, and see if it gets some interest, right? And we might add it in, or a pull request. If it's a non-trivial thing, it'd be better to have a pull request for it. But, so that's that's the story there.
Okay, and so do you think that instead of doing this back and forth between NumPy and PyTorch, say, you could implement what's needed by SciPy optimize? So I guess it's basically matrix vector products, vector multiplication or inner products or things like this, like basic linear algebra operations. And if you have access to all these linear algebra operations, then you'll be able to implement what's implemented in SciPy.
Mm-hmm.
So the idea would be to not to use NumPy at all, but just implement the interface to common linear algebra operations.
I mean, I think what Brandon was asking about, like just re-implementing all those algorithms like in PyTorch or TensorFlow.
No, not exactly, because I don't really know how it's implemented in SciPy, but
a lot of them are actually like in Fortran. they're some of them are like they've been around for so long. Yeah, they're a Fortran and like it's a wrapper on that. So it's like a
wow. Okay.
Yeah.
Okay,
it's like
it's just impossible.
Yeah. It doesn't look fun. No, to try to. I think the best thing to do is like treat it as a black box and go, okay, well, this is a black box. It tends to work pretty well. So we're just going to treat it as such. I think some of those methods might be implemented in NumPy, and then I think some of the other ones are actually implemented in Fortran. And it's like a wrapper around that. I just haven't really spent much time trying to dive into the internals of it because it's like I just don't want to touch it. So that's the story there on those.
Okay. You're open to pull requests then, so that's
for sure. I think somebody asked for something called tracks or something. That's like some souped up thing on Jax, but asked them to put a pull request and they never did it though. I don't know.
Okay, well, unless there are other questions, let's please thank Ryan for taking the time to share this library with us today, and hopefully we'll put the slides up in a little bit. Ryan, thanks again.
Thank you for having me.
May I have just a quick question?
Okay.
Just very quickly. Do you know if any of these algorithms are actually implemented with GPU acceleration? Maybe not all of them that SciPy supports, but at least some of the major ones. I'm not really insider of the field, so I'm just curious.
I suspect not, because I think a lot of these implementations are pretty old from before GPUs were popular. So I think a lot of it comes from, if it's a very expensive function to compute and get the gradient of, you do that on GPU and then do the parameter update on CPU, which is usually the algorithm. Usually the algorithms themselves are very cheap to run. It's just the computing the objective function that's expensive.
I see. So when you were running, for example, the experiments that you were showing, like the transfer of all the gradients from GPU back to CPU was not too much of an issue. Like it's
no, I don't think it shouldn't be an issue, because it's just the final answer. And if it's a small, I mean, if it's a massive parameter space, it will be an issue. But if it's just like a few hundred, numbers, it's not that big of a deal.
Yeah, I see, because you probably don't have to like get everything, just the gradients at the last.
Yeah, just to get the final answers.
Right? So, like, and it's probably not that much bandwidth, right?
It's just probably like a kilobyte of data, so it's probably not that big a deal. So,
thanks.
Yeah. So, thanks again. I mean, unless there's another last-minute question before I hit the end, I'll hit this. I can hit the stop share too. Unless there's another last-minute question right before I hit the leave meeting button.
No, I think at least not for me.
All right, sounds good. Thanks for having me again. I'll sign off now. That's it. Bye.